Hi everyone, Mr. Webb here showing you the very last thing that we're going to learn in Integrated Math 3 this year, which is how you can solve equations when you have a radical function like this one right here, the square root of x plus 1, equal to a linear equation. So I'm going to show you guys how to do this with algebra, graphing, and tables to give you guys an outline of how to do this. So let's go ahead and our essential question today is going to be how can we solve radical equations using algebra, tables, and graphs. So we'll go through each one of those things. So what we're going to do is we're going to do algebra first. So when we take a look at this function, we've got the square root of x plus 1 equals x minus 1. Now our typical algebra moves unfortunately aren't going to work, like adding 1 to this side and subtracting x, because of this square root thing. So in order to handle our square root, what we're actually going to have to do is we're going to have to square both sides to get rid of the square root. So as you can see here, we're squaring this entire side, and if I square this entire side by algebraic reasoning, I'm going to have to square this side too. So all it's going to do is on this side, the squaring is going to drop that square root symbol, but on this side, I'm going to have to treat that by multiplying a binomial. So most of us, our chosen method is by using the Punnett square, but you can FOIL this as well. So we're going to do x minus 1 times x minus 1. You can see here we've got x minus 1 times x minus 1, which our result is going to be x squared. Combine these two like terms to make negative 2x plus 1. So as you can see that we dropped the square root on this side, and our right side of the equation is going to be equal to x squared minus 2x plus 1. So moving on, what we're going to do is, as we can see here, that this actually turned kind of into a sort of quadratic equation. So we know the way to solve quadratic equations is we need to move all terms to one side. So we're going to have to move this x and the 1 over to the right side, and the way we're going to do that is that we're going to subtract x from both sides and also subtract 1 from both sides. When we do that, we're going to have the x squared, nothing happened to it because there was no x squared term on the left side, but negative 2x minus x is going to give us negative 3x, and plus 1 minus 1, that's going to give us 0, so there is no c term here. So hopefully you guys remember from our old quadratics unit, we're going to solve this by factoring or our preferred method. So you could use quadratic formula here, but honestly factoring is going to be much, much simpler. You can think about this as a GCF, that I could pull out the GCF of x squared and negative 3x, or you could think of it like factoring trinomials, two numbers that multiply to 0 but add to negative 3. So I'll think about it more from the GCF perspective, which means I'm going to pull out an x from both sides. So you can, or excuse me, from both terms. There is no other number to pull out, so that's going to work for us. So we've got 0 equals x times x minus 3. And then that would mean our two solutions are x equals 0, and then solving this factor, x minus 3 equal to 0, we're going to get our second solution as x equals 3. So as of right now, we say our solutions are 0 and 3, but there's actually going to be a problem with these particular problems, and we're going to have to find that out by actually plugging in those two solutions into the function. So an important part of these kind of weird radical functions is we're going to have to plug in to see if they actually work. So we're going to try 3 first. So we've got our original functions right here. And what we're going to do is we're going to try putting 3 back into the solutions. So we're going to replace both x's with 3. So we've got root of 3 plus 1 equals 3 minus 1. That's going to give us root 4 equals 2, which of course we know that's correct. 2 equals 2, so we're good to go here. So 3 is definitely a solution of this, this equation. But if we take a look at the other one, let's go ahead and see what happens actually when we try 0. So if you'd like, pause the video and check it out yourself. But let's see what's going to happen here. So we're going to, just like we did in our last slide, we're going to go ahead and replace the x's with zeros. Instead of 3 this time, we're going to replace it with 0. And then we're going to get the square root of 1 equals negative 1. Square root of 1 is equal to 1, so we get 1 equals negative 1, which is just not a true statement, so this is not a solution. So 0 is not a solution, and the big takeaway from this is that you must always check your work when solving these type of equations. So the only solution to this, this set of equations was 3. So and this was, like I said, despite the algebra showing that the solutions were 0 and 3, you have to go back and check them. So if that's a little tough for you, you might want to actually try, I've got an alternative way for you, and that's actually going to be using tables and graphs. Oh, how'd that get there? So what we're going to do in order to solve tables and graphs, you're going to go into your y equals in your calculator. Okay. We're going to go into our y equals, and in our y1, we're going to put the square root. Let me just double check what the formula was. So it was x plus 1, so the square root of x plus 1. And then in our y2, we're going to put the other equation, which was x minus 1. So we'll go ahead and start with the graph first. So just like always, I think it's a good place to start with the standard viewing window by hitting zoom and then 6. And you can see this gives us a pretty decent picture, so there's no need to change anything. So as you can see visually, we've got, in order to find this solution, we'll find the point of intersection. So second trace, intersect, and you can see there's only one point of intersection over here. And to find an intersection, we're going to get as close as possible and then press enter 3 times. And you can see we get our solution of 3. Now, what actually ends up happening here is you can see that we got the same thing, that we have a solution at 3, but I want to show you guys just what happens at 0 right here. So as you guys know, you cannot take the square root of a negative number, but if you could take the square root of a negative number, this graph would kind of continue along this sort of path this way, and we would pass through at 0 right here. So that kind of explains our missing solution. So that's how you guys find it and verify your answers using the graph. Okay, so finally, last but not least, is the table. So just like always, what we're going to do is, I think starting at -5 is fine, but you could start at 0. It's completely up to you. And going by ones is a good call here. So we're going to press second graph. And as you remember, I said you couldn't take the square root of a negative number, which shows you guys why we have all these errors here. But essentially, when it comes to the table, what you're really looking for is where the two y values are the same. And it shouldn't be much of a surprise to you since we've already found it with algebra and with the graph, but they are the same at 3. So both functions are equal to 2 at 3. So that explains how to solve this type of function all 3 ways. Now, just to prove that you guys know what you're doing, your assignment for today is going to be each of these 3 sets of a radical function equal to a linear function. I would like you guys to solve them with algebraic reasoning, tables, and graphs, and that is your assignment, and good luck, and let me know if you have any questions.